I don't know what a force does, what a torque does yet, but I do know what a force does. A force is capable of changing the linear momentum of a system. Okay? So let's, for simplicity, let's say I only have one point, one object, point mass, moving with linear momentum p. Okay, so I have, let me draw that point here. Here's a point of mass m, speed, velocity v, so that's got a linear momentum of mv. Say mv, p equals mv. Okay, and it is subject to a force. It's subject to a force at this point. Say force at this moment is like this, F, external, the net force. Now, I'm going to observe the motion of this point from a certain reference line, and reference point, here's my reference point, O. Okay, what I'm going to do is let me draw a line connecting the point of interest and the point to, reference point to the point mass. Let's call this vector r. I want to know from torque's point of view, you know this force provides a torque at about this point, right? What does this torque do to the motion of the object? Well, we know what the force does, and torque is just r cross f, so why don't I take r cross f on this side and r cross dp dt on the other side? Let's do that. R cross and r cross. This side is just the torque, right? The torque exerted by this external force measured from this reference point. The other side is r cross dp dt. What is p? P is m times v. Let me simplify the other side a little bit and see what we get. Okay, this is r cross ddt of mv. Okay, how does one simplify it? Well, I'm going to simplify it by actually adding a term first. You will see why I do that. I'm going to add a term here, and that term is dr dt cross mv. Okay, look, what's dr dt? Isn't that v? What's v cross mv? Well, v and v are parallel to each other, so the angle between them is 0, so this term is actually 0, right? I have added a 0 term. Of course I can do that. I can always add something which is equal to 0 to whatever we have already. But why did I do that? Well, here's why I did that. You see, if I call this A, call this B, what you have is A cross dB dt plus dA dt cross B. What do you think that is equal to? Well, remember the formula you learned in calculus, d dt AB. What's that equal to? That equals dA dt B plus A dB dt. Remember that? Okay, this works even if A and B are both vectors and you take A cross B instead of just A times B. Okay, but be careful here. If you're doing A cross B, okay, if you're doing ddt of A cross B, I'm going to use a different color to highlight this cross symbol. Both of these are vectors now, okay? You can do just that, but be careful. When you do A cross B, make sure you always put A ahead of B, because when you reverse the order B cross A, you'll get a negative sign. Okay, so be careful here. Here you can write B dA dt. Right? Here you cannot write B cross dA dt. You must take dA dt cross B, because A has to be ahead of B at all times. That's dA dt and B cross, okay, A is always ahead of B. The next term is A and then dB dt. Again, there's a cross sign between them, and you put A ahead of B. Okay, that's the formula we can use here. You see, you call this A, you call this B, right? This is A dB dt and dA dt cross B, right? So you combine them, what do you think you're getting? Aren't you getting ddt of A cross B? A is R, B is mv. Isn't that R cross mv or R cross P? Right? Okay, so basically we rewrote the right-hand side into ddt of r cross p. The left-hand side is torque. The right-hand side is the rate of change of this quantity r cross p with respect to time. You know from the dynamics of translational motion, external force equals rate of change in linear momentum. Here I have external torque, right? What is that equal to? The rate of change of this quantity. So clearly, by analogy, this quantity r cross p should be called angular momentum. Okay? In fact, let me then define a quantity called L. It is defined as r cross p. That is the angular momentum of a single point mass with linear momentum v. Linear momentum p. And the location vector, okay, the position vector of that particle is r, measured from the observation point to that point of interest. Then we have the angular momentum of that object, measured from here, is equal to r cross p. That is for a single point mass. Okay, so we rewrote Newton's second law. Instead of looking at how the linear momentum changes, we now look at how angular momentum changes. Okay, so with that, I can write torque equals dl dt. Right, this r cross p is L. This is just torque. So I have this. External torque equals the rate of change of L, which is called angular momentum. This is totally analogous with the translational case, which says that external force equals the rate of change of linear momentum. So, by analogy, we should call this angular momentum. Okay, I was assuming that we only had one point mass. Okay, what if I had a collection of particles, a whole bunch of particles? They may not be in a rigid body. There could be just a piece of cloud, which is made of a whole bunch of water drops. Okay, every point can have a totally different direction of motion, whatever. They don't have to be a rigid body, whatever. How does one expand this formula beyond a single point? Well, we can do what we did for, in chapter 9 for, a motion of a whole bunch of particles, a system of particles. What we can do is for each of them, for each particle, I can write the torque on that particle equals dl of that particle over dt. Right? I write one equation for each of them. And then I'm going to add all these equations up. Okay? Add all the particles up. And of course, on this side, I get a total torque, net torque, on the entire system made of all these particles. On that side, I just have to add all the contributions up, right? This r sub I cross p sub I, that is the linear angular momentum of the ith particle in your system, right? And if you have a whole bunch of particles, just add them all together. This is the most general expression, the most general version of the angular momentum of a collection of particles, be it a rigid body or not. I say it's the most general version, but it does not remotely look like something we would expect from analogies with linear momentum, because linear momentum is m times v, right? So if you think that p and L should be analogous, but p is equal to mv. Now shouldn't L, if you believe the analogy, n becomes what? I, right? And v becomes what? Omega, right? Shouldn't be equal to I times omega? And this looks totally different. It's r cross p is totally different. Okay, so the question is, when can this general expression reduce to something we expect out of analogy, that is I times omega? Okay, first thing first. Omega is a quantity that's relevant when you have rotation. Okay, when you have a piece of cloud, it may not be rotating. You just get a whole bunch of particles flying all over the place. Okay, and the reason why you can write something like I times omega, one thing is clear. If you think that you can treat the entire object, angular momentum, as I times omega, there must be only one omega value for every point on that object. right? Otherwise, which omega do you use, right? Which omega do you use? So I'm looking at an object rotating as a single piece with the same exact omega for every point on that object. Of course, a rigid body, a rigid object will be a perfect example. It's rigid, therefore omega's got to be the same. Okay? And there are other cases when the object is not entirely rigid, and yet every point on that object can still move with the same angular velocity omega. Let's see what happens when you look at a rigid body. Okay? When you look at a rigid body, then if it's rotating about a fixed axis, it doesn't have to be fixed axis, but let's say just for this one moment it's rotating about this particular axis, okay, with an angular velocity omega. Omega, of course, is the same for everybody because it is a rigid object. Okay, at this very moment, look at the ith particle. The ith particle is located a distance, with a position vector r sub I from the axis, and it is moving with a velocity v sub I. Okay, this of course is 90 degrees because this particle is actually doing a circular motion, right? Doing a circular motion about that point O. Okay, what is r sub I cross p sub I? P is the linear momentum of this point, which is mass of the object times its velocity. Okay, so first of all, r cross v. R cross v is, both r and v are defined, are to, drawn to be within this plane. Okay, so r cross v is perpendicular to this plane, and that goes for every point, within this plane. So imagine I have a three-dimensional object. I can always cut it into slices, right? I can always cut it into slices. Each slice is a plane that is perpendicular to the axis of rotation. What I'm doing is I'm looking at this slice first. For every point on that slice, within that slice, r cross v is always perpendicular to that slice, which means it's along the direction of omega. So I can add all of these individual angular momenta in the same direction because they're all pointing this way. They're all pointing in the direction of omega. So I can add them like scalars. Okay, and that is true not only for this slice, for every slice that's parallel to omega. So for the entire object, basically, for the entire object in rigid object, every one of them contributes an angular moment in the same direction, which is the direction of omega. What is the magnitude of the angular momentum from this little piece? Well, that would be r cross p. R and p are perpendicular to each other, right? Because, it's r is radial and p is along the direction of v, which is tangential. So ri cross pi, the magnitude, what is that equal to? It's just ri pi times sine 90 degrees, which is what? Now pi is mvi, so that's ri mivi. Next, let's express vi in terms of omega, because after all, every point has the same omega if it's a rigid body in rotation. So what is vi equal to? It's omega times ri, right? So this is ri times mi times omega times ri. So I get ri squared, mi, ri squared omega. That is the magnitude of the angular momentum of this little particle. Now remember, every single particle contributes an angular momentum in the exact same direction. Okay, so as far as the angular momentum for the entire object is concerned, all I have to do is to sum over all these magnitudes because they're in the same direction. So the angular momentum of the entire object, as far as the magnitude is concerned, is just, the sum over I for everything throughout the entire object. Take a good look at what I got here. Okay, now what is this? R sub I is the distance between that point and the axis of rotation. Isn't this I the rotational inertia about this axis? So yes, indeed, we get L equals I omega. It is true, but there is a condition, and that is every single object at this moment must be rotating about the axis at the same angular velocity. Okay? Every single piece belonging to that object must be rotating at the same angular velocity. A rigid body certainly satisfies that. So this is not the most general case, but it's an important special case. Here is the magnitude. What about the direction? Well, the direction is along the direction of omega, so therefore I'm going to simply attach vector sign here. L and omega have the same direction. So indeed, L can be equal to I times omega. So, to recap that, I found that L can be equal to I omega provided that omega is the same for every point on that object. Like I said, if it's a rigid object, that certainly works. Okay? Omega is the same. Is it possible that the object may not be rigid, yet omega is still the same for every piece on that object? Yes, it is still possible. For example, if I look at, if you look at a ruler, okay? Let's say I have a ruler. I set this ruler into rotation. Okay? The ruler is a rigid object. Of course, every point has the same omega. But suppose I have a bead. I have a bead, and this bead can slide back and forth on the ruler. Alright? Now, as the ruler turns, the bead is free to go inside, it go inward and outward. Alright? It can go inward and out, but it is still on that ruler, which means it is rotating together with the ruler. It's just that on top of the motion, on top of the rotation, the bead can also go forward and backward radially. But the radial movement of the bead does not change its omega, right? Omega is when you turn around like this. So let's take a top view, okay, a top view of the situation. The ruler is first of all like this, and here's the axis of rotation, and the bead is, say, momentarily, it's here. The next moment, okay, the ruler is now like that, and the bead has moved, say, to the tip, to here. Okay, the ruler has turned this much angle. What about the bead? Well, the bead did two things. First of all, it went outwards, but secondly, it also turned through the same angle. You see that? Okay, going in and out does not change omega. So the bead and the ruler has the exact same value of omega. However, because the bead actually moved in and out, it can change the angular the rotational inertia, I, of the system. This is not a rigid body as a whole, because the bead can actually, slide against the rest of the ruler. It can do that. It's not a rigid body, but it still has the same omega, so I can still apply this formula. So it is possible to have a variable, even deformable object with variable I, as long as omega is still the same for every part of it at one given moment, then L is still equal to I omega. Suppose that is the case, okay? Let me then apply torque equals dL dt. And then L becomes equal to I omega, right? How can I simplify this? Well, I have two terms. The first term is I d omega dt, right? The second term is omega di dt. Look at the first term here. The first term is just I alpha, okay? So torque equals to I alpha, as we expected before. It's like F equals ma. But F equals ma was not a general formula. It was true only if the mass did not change. Here the same thing. Torque equals alpha is not a general formula. It is only true if I, the rotational inertia, does not change. And what if it did? Then you have a second term. Okay, let me use a different color for the second term. Plus omega di dt. You see, this second term takes place only if I changes. Okay, like in this case, for example, the bead went inward and outward. That's going to change I. Okay, that's going to change it, so you would have a second term like this. This is the most general expression for the torque theorem, more general than what we had before for fixed, for rigid object, provided that the object as a whole still has the same angular velocity. Okay, it is now deformable, but omega must be the same for every part of it. You would have a second term due to the change in the angular momentum. I mean, the rotational inertia. We'll look at examples when this term is an